Greetings and welcome to Distillate. In the previous few lectures, we have dealt with multiple problems dealing with ordinary differential equations, where we have developed ordinary differential equations and solved them numerically using Python. Um, so we've been able to deal with problems related to normal single variable ordinary differential equations. We've talked about coupled ODEs in the previous tutorial, multiple ODEs together, and so on and so forth. So this is the last tutorial on ODEs, and this is another set of ODEs that can be developed for the problems related to what we chemical engineers deal with very often, and that's called as multiple reactions. So the a lot of you must be familiar with multiple reactions. So I would just give you an introduction to this, and we'll try to solve the ODEs that we develop for these systems using Python. So multiple reactions could be of three kinds. There could be series reactions, there could be parallel reactions, and there could be series parallel reactions, right? And as the name suggests, series reactions are reactions taking place in series. Parallel reactions are reactions taking place simultaneously, so or parallelly, right? And series parallel reactions are a combination of these. So there could be some reactions taking place in series, some reactions happening parallelly, and so on, right? So, and there could be more complex reaction networks that could be developed using these systems, right? So, let's talk about these kinds of systems and let's try to develop ODs for these reactions. So let's start with, say, series reactions, right? So if let's say we have something of the kind A, B, C, and the rate constants for these are K1 and K2. So the simple ordinary differential equations for A, B, and C could be written as dCA over dt equals to minus K1CA, considering elementary reactions. Although you don't need to have elementary reactions for, like, you don't need to make these reactions simple enough, because using Python, you can do multiple things. So if you're if you're solving these ODEs numerically, you don't really need to stick to problems that can be solved analytically as well. But let's just start with simpler problems, and then maybe you could develop more complex problems with various sort of complicated rate expressions and so on. Right? But this is a good thing to get started with. So we could have dCA by dt equals to minus K1CA, dCB by dt equals to K1CA minus K2CB, and we could have dCC by dt equals to K2CB, right? Now, these are of course coupled ODEs once again, but we could also sort of solve these problems using uh, what is called as a stoichiometric matrix, because over here we just have a set of three reactions, but we could have multiple reactions taking place in series or parallel or so on and so forth. So we really want to try and solve these equations, these reactions, as wonderfully as we can. So let's introduce the concept of stoichiometric matrix through this problem, and then we could generalize it for a system as complicated as this, for instance, right? So the stoichiometric matrix is actually developed for multiple reaction systems. So for example, we have this reaction A to B, B to C, right? This is a series reaction. But if we just break down the system, and we could write this as reaction number one, A to B, and reaction number 2, B to C, right? Now, what we could do is we could make a matrix for this particular system of reactions wherein the rows represent the reaction number, okay, and the columns represent the element. So for example, A, B, or C. So there are three elements in, or basically three species could be represented in the columns, right? So over here in this matrix, the first row and the first column would represent the stoichiometric coefficient of A in the first reaction, right? And remember, the stoichiometric coefficient for a reactant is always negative, while of the product, it's always positive, right? So in the first reaction, the stoichiometric coefficient of A is 1, but since it is a reactant, therefore this is -1, right? For B, because this represents A, this represents B, this represents C. So for B in the first reaction, we have 1 and there's no C, so it's going to be 0, right? Similarly, for the second reaction, the coefficient of A is 0. The coefficient of B is -1. It's a reactant. And for C, it's 1 over here, right? So that's the stoichiometric coefficient of, the stoichiometric matrix for this particular system of reactions, right? Now, what is the advantage of this type of a system? So this is a 2 cross 3 reaction, the 2 cross 3 matrix, right? So if we multiply this by, let's say, a 1 cross 2 matrix, right, from the left hand side, we would get a 1 cross 3 matrix, right? So the question arises, what 1 cross 2 matrix would be multiplied by from the left hand side? So maybe let's multiply it with what is called as the rate vector. Okay, so this is R, which is a 1 cross 2 matrix, a row vector, right? So R1 and R2, because there are two reactions. So this represents the rate of the first reaction, and this represents the rate of the second reaction, right? So over here, the rate of the first reaction is just K1CA, right? And the rate of the second reaction is K2CB, right? So we could have the rate of the first reaction and the rate of the second reaction, and this becomes a 1 cross 2 matrix, right? This becomes a 1 cross 2 matrix, right? So now if we multiply the rate vector to the stoichiometric matrix, we would end up getting R times, let's call this a stoichiometric matrix. So R multiplied by S would just give us minus R1 plus R2. So, sorry, this would be, sorry, it's going to be minus R1, then R1 minus R2 and plus R2, right? That's going to be the 1 cross 3 matrix that we get. And if you substitute K1CA in place of R1 and K2CB in place of R2, you will realize this actually becomes minus K1CA, then K1CA minus K2CB and K2CB, right? And if you see, this is nothing but the RHS of this set of ordinary differential equations, right? It's this, this is the reason why stoichiometric matrix becomes very important, because just by seeing individual reactions and the stoichiometric coefficients in the individual reactants, you can get the RHS of the ordinary differential equations. And then it becomes easier to deal with these kinds of systems, uh, right? So let's call this vector as F, right? So now all that you have to do is, in order to solve the ordinary differential equation, you have to say that the concentration vector, which is just Ca, Cb, Cc. So the concentration vector at, the concentration vector at time t plus delta t is equal to concentration vector at time t plus delta t times the stoichiometric, the F vector evaluated at time t. That's all that you have to do. This is once again the Euler's explicit method. If you do it using the Runge-Kutta methods, you could substitute the formulas for Runge-Kutta methods, but this just makes it very, very simple, right? And that's all you have to do. So the overall objective then becomes to formulate the F vector somehow, and finally to evaluate the concentration vectors just for all the time points, right? So you could do this for much more and more complicated systems, but this equation remains the same. So even if we deal with a system of this kind, we would still end up getting this particular equation. However, the only difference would be that the concentration vector and the F vector would be different, of course, right? So all that we have to do is this, right? So let's just try to do the same thing in Python, right? So what you have to do is you have to formulate the rate vectors in each iteration. You have to formulate the stoichiometric matrix. You just have to formulate once, but the rate vectors have to be calculated at each matrix, at each iteration. You have to calculate this matrix multiplication, and finally you have to evaluate this F by that matrix multiplication, and then use that to calculate the concentrations at the next time point. And once again, you need one initial condition for each of these concentrations. So at t equals to 0, the concentration vector becomes Ca naught, Cb naught, and Cc naught, right? So that's all that you need. And now you can solve any kind of complicated multiple reaction system using Python, right? So let's go to our Python slider and let's try to evaluate these things, right? So over here we have the parameters, our rate constants. I've just given some numbers over here. One thing that I want to do is I want to formulate the stoichiometric matrix. So we could have this as np.array. And now remember, this is going to be since this is a system that we are using, we'll have 2 rows and 3 columns. So basically it's going to be a 2-dimensional list that eventually becomes a NumPy array, right? So we are going to write it as the first row. So it's going to be the first reaction, comma, the second reaction, right? The stoichiometric coefficients, the first reaction, and the stoichiometric coefficients in the second reaction, right? That's how you formulate this 2D list, right? So that's going to be -1, 1, 0, and 0, -1, 1. So minus 1, 1, 0, and this is going to be 0, minus 1, 1, right? So this is the stoichiometric matrix that we have formulated. And after that, there's the rate array that we'll have to formulate. So the rate array, this is the initial rate array. But before that, we also need the initial concentrations. So the initial concentrations could be, let's say, C, we start with, let's say, A. So we could have 1 mole per liter of A, and everything else is 0 right now, right? So that's np dot array 1, 0, 0. And over here, this is going to be the initial rates. So that's going to be minus K1. The first reaction has K1 times Ca, which is just C0, right? And the second reaction has the rate K2Cb, so K2C1, right? That's there. So that's the rate array, right? Now this is the initial rate array, but you will have to evaluate this at every iteration, right? So that's going to be the case. And we'll just make C as the array over here. So here we are just going to evaluate this at the last concentration. This is the same logic that we used for all the other ordinary differential equations, right? So that's how we evaluate the rate array. And finally, F is nothing but the matrix multiplication of R and S. So maybe we are going to say NP dot matrix multiplication R comma S, right? That's what we are going to do. Okay, so we have the F array over here, and hence actually we could just evaluate this within the loop over here, right? And then we could say C dot append C minus 1 plus dt times F, right? That's it. So this basically is F evaluated at the previous iteration, and that's it, right? And now C has been appended, and we could also append the time array over here. So t minus 1 plus dt, and that's it. So that's the solution, and we could now plot this thing. So just like we've been plotting. So for I in range len C, C is small. So len C, because that's how many of them we have. And before that, we convert C into a matrix, just so that it's easier to extract data. So C equals to np dot array C. And after that, we'll say plt dot plot t comma C. And now we are going to evaluate everything. Like we are going to say all rows, because all rows means all time points, comma the ith column. So ith column represents A, B, or C, right? So, and label, we could just put anything right now. So let's just put it as string I, right? You could do some different, different coding tricks to add A, B, or C over here. For example, I could say maybe I could make a label list and I could say this is A, B, and C, and I could just say this could be label I, right? So that would actually consider this as the label. And finally, plt.legend and show, right? So we can do this, and we've got this result over here. So as you see, for this case, we don't really see much of B, and that is expected because the second reaction is a lot faster compared to the first reaction. But let's say we reverse the reaction rate constants. We'll see a different thing over here. So now we see a lot of B's formed before it actually goes ahead and forms C. And if we make the second reaction even slower, we'll see that this B stays with us for a much longer time. So we could do all of these tricks and study these reactions as much as we want, right? So this is a very simple case where we just evaluated this thing. Now, the reason why this becomes very useful is because now you could just talk, this method becomes very easy because now you could just consider them to be um, any kind of reaction rates, and you could still solve them. So for example, let's say we say that instead of being a first order reaction, let's say this could be a square root instead of a first order reaction here, right? And let's say this could be a second order reaction here, so it could be something like this, right? So we could still evaluate this without changing anything. The only thing that we had to change over here was the rate equation over here. So now if we evaluate this, we see that B is formed this way, C is barely formed, right? Maybe if we make the rate comparable, we see this kind of a system. So the point is that now we can deal with different kinds of operations. We could deal with different kinds of problems, and we would still end up getting solutions. So these systems, for example, a half order reaction or a second order reaction is a bit more challenging to solve, but because of the fact that this particular thing makes it so easy, the numerically it becomes so easy to solve, we can actually do a lot of cool things, and we could study these systems over here, right? So now, since we can do this for a series reaction, we could definitely do this for parallel reactions. So I would highly encourage you to conduct the same analysis for a for a parallel reaction. But let's move on to series parallel reactions, because that is something that is very complicated, and this method makes it a lot easier to deal with it. So let's deal with this kind of reactions, right? So we have the series parallel reactions. Say A goes to B, goes to C, which eventually ends up forming B and E, right? So now in this, we would have four rate constants, K1, K2, K3, and K4. And once again, the rate arrays would be, so this is the rate vector is going to be, so this is the first reaction, this is the second reaction, this is the third reaction, and this is the fourth reaction. So the rate vector for this becomes K1CA, this is the rate for the first reaction, K2CB, the rate for the second reaction, K3CC, the rate for the third reaction, and K4CC, the rate for the fourth reaction, right? And the stoichiometric matrix over here, since there are four reactions, so we will have four rows, and there are five species over here, so we'll have five columns. So for the first reaction, we just have A and B, so it's going to be -1, 1, and rest all zeros, right? The second reaction has B and C, so 0, -1, 1, 0, 0, right? The third reaction has C and D, so 0, 0, minus 1, 1, and 0. And the fourth reaction is seen E. So 0, 0, minus 1, 0, and 1, right? And we just need to multiply rate and the uh, reaction S, right? The stoichiometric matrix S, right? So all that we have to do is change the stoichiometric matrix for our system as well as the rate expression over here, along with, of course, since now we have multiple species, so we will have more and more concentration values in the concentration array, but a few changes in this code and we'll be done. So let's say K1, K2, we'll add other K3 and K4. We'll change the stoichiometric matrix. So the first is minus 1, 1, 0, 0, 0. So minus 1, 1, 0, 0, 0. The second is 0, minus 1, 1, and then 0, 0. The third is 0, 0, minus 1, 1, 0, hopefully. 0, 0, minus 1, 1, 0. Yeah. So 0, 0, minus 1, 1, and 0. And the fourth one is 0, 0, minus 1, 0, and 1. Right? That's the stoichiometric matrix. Hopefully the parentheses are fine. And after that, this becomes 0 and 0. Sorry, there are 5 species, 0, 0, 0, right? And after that, we'll change the rate array over here. So there are going to be, since there are 4 reactions, so we'll have 4 rates. So the first one is going to be K1 into Ca, which is C minus 1, 0. The second one is going to be K2 times Cb, which is C minus 1, 1. Then the third is K3 into Cc, which is C minus 1, 2. And the fourth is K4 into Cc. And that is, once again, C minus 1, 2. Right? So that's the rate array, and we are done. And we don't have to do any changes. With some things will cost me some manipulations here, but that's it. So now if we solve this problem, we'll see all of these reactants being visible. And the main thing that we see over here is that eventually probably it's D and E. I think D and E are forming the same way, but let's say we reduce the rate of the second reaction greatly. So in this case, the rate of the second reaction over here, the fourth reaction over here, which is C to E, we've reduced it. So we would probably see less of E being formed. And let's just see that over here. So now we see E, the D formed is a lot more compared to E, right? If we change, let's say, the second reaction, we could see a more, we could see a more different behavior over here. And yeah, we could play around with the rates of these reactions and so on and so forth. With parallel reactions, we've also seen that negative order reactions have different effects than positive order reactions. So let's just consider negative order reactions over here. The next two we've made K3 by C and K4 by C, which means these now have negative orders. And now, okay, this has gone wrong because there's a divide by 0 thing that we got. So maybe if I make this very, very small initially, this would probably not happen. Yeah, so over here, basically we see this is also not correct. So C has gone to negative concentrations. So this is also not correct. And that is probably because this has numerically blown up. So I think we'll have to talk about stability of these ODEs and whether these are integrable or not. But I think you have got some basic idea of how to solve these ODEs. So let's just get back to the same beautiful set of ordinary differential equations that we were trying to solve. And yeah, so this is the solution over here for these kinds of problems. And yeah, this becomes more and more much faster. So you could play around with these things. Negative order reactions are definitely some things that would need some bit of extra manipulations, because the terms towards the RHS will start to blow up for very low concentrations. But for positive order or zero order reactions, it would actually work very well. So hopefully you will be able to play around with this kind of system. So I'll provide this code to you people. Make sure that you know how to make the stoichiometric matrix. So basically you just write down the reactions separately, and then mention the rows represent the reaction number and the columns represent the species here. And the reactants have a negative stoichiometric coefficient, and the products have a positive stoichiometric coefficient. So once you start dealing with these kinds of reactions, it becomes very easy. And if, let's say I make reactions, let's say I make this reaction an equilibrium reaction, or a reversible reaction, not equilibrium, a reversible reaction. So that adds an additional reaction, D to C, right, to my system. So in that case, there would be an additional rate over here, which would just be K5CD. And because of that, there's going to be an additional row in my, an additional row in my stoichiometric matrix, which is going to be just 0, 0, 1, minus 1, 0, right? That's going to be an additional row, and you would still end up getting the same result for your problem, right? So the main thing that I want to emphasize on is that you could deal with various such problems, you could deal with various such things, and you could just break down your problem into this form, where you evaluate the rate vector and the stoichiometric matrix, and you are done. So a lot of these series reactions, parallel reactions, multiple reactions problems, you'll be able to deal using this simple set of code over here. So hopefully I will provide this code to you people in the Google Drive. So please play around with this code, maybe try to implement better ways to solve these problems. If you have better suggestions to implement, say, negative order reactions, please put them up in the comment section. I would love to learn more about these things from you all. And just hopefully you people find this amazing. In case there are other ODEs that you want me to cover, you could mention them in the comments. You could also mail me. I've provided the mail ID in the description. But this is the final tutorial that we are going to deal with for ordinary differential equations. We would, of course, keep on solving certain other ODEs as time passes by. But for now, let's move on to further topics in Python and numerical math. So hopefully you enjoy it and keep practicing and keep playing around with the codes that I'm providing you. And obviously, I would love to hear if you can make them even more efficient. You can implement better things in these codes, play around, and just hopefully we are able to solve more and more such interesting problems using Python.